So before we start with today, let us have a quick review of what we have seen day before yesterday. I hope you had a sufficient time, 1 day gap, to do some extra numerical problems and have a quick revision. So if you work out a lot of numerical problem, then only you will be able to mm, perform better. Okay, we were looking at some of the types of signal. So we have seen what are meant by periodic functions. So the most popular is the sinusoidal function, which we have seen, and I have explained what is the concept of time period, which is normally represented by capital T in our course. And what is omega? It's called angular frequency. How they are related like that. Then periodic pulse, how it could be represented, we have seen. Then we saw what are sinusoidal functions in detail. So a time period capital T is equivalent to a total phase shift of 2 pi. So they are related by this relation. Capital T is equal to 2 pi by omega, where omega is the angular frequency. And then we saw the concept of time shift and phase shift. If you are considering any time shift tau instead of capital T, that is the period, we can write the general expression as theta by omega. When tau becomes equal to capital T, then theta becomes equal to 2 pi. So that we have seen that relationship. Then we have seen the concept of time shift and phase shift. Because theta and tau are related like that. So on the right hand side is shown what is meant by a time shift. So we consider a function, a sinusoidal function, a sine omega t. So we can either delay this function. So delay means we are shifting it in the time domain towards the right side. So how can we delay? We can delay it by subtracting a time quantity tau. So a delayed sinusoidal function could be written as a sine omega t minus tau or a cos omega t minus tau. Okay, so that is called delay. So why it is called delay? Because initially the signal should have started at 0, but now it is starting at a delayed time which is equal to tau. Okay, so tau can take any real values like 1, 2, 3, etc. or 1.5, etc. Okay. Similarly, we can advance the sinusoidal function, which is nothing but equivalent to shifting the function towards the left side of the time axis. Okay, so we are advancing. It is called, otherwise called advancing. So how can we advance it? By adding a time quantity tau, so that now the signal starts, instead of 0, it is starting at say minus tau. Okay, so it is starting early. So that with that perspective, if you view, then you will be able to remember what is meant by time delay and time advance. Now you know we have told like tau is related to theta also. So because by this relation, tau is equal to theta by omega. So we can do, when you do shifting in the time domain, we can understand that it is happening in the phase domain also. For example, in phase, it is not called delay. In phase, it is called phase lagging. That is when we create a delay, then there is a corresponding shift in the in in the waveform with respect to the phase, which is called as the phase lag. Okay, so that could is represented by, for example, when we have a horizontal function a sine theta, then a sine theta minus phi is called a delay or lagged function, where phi is called the um, angle with which, or the phase with which it is lagging with respect to the original function, that is a sine theta. Similarly, when we when we shift the function with respect to time domain, advance it, correspondingly we can have a phase lead happening in the with respect to the phase, if we see. So it means that instead of starting at the function is starting at 0, it is starting at say minus 5. Okay, so it is starting early. So that could be understood by with respect to these graphs. I hope now the concept of shifting with respect to the time axis and with shifting with respect to the theta is clear to you. I hope there is no any doubt. Okay. So shall we move forward? After that, we have seen what is the period of a function which is obtained by combining two or more periodic functions. So what is the time period if we combine two periodic functions, say v1 of t and v2 of t? So that we will get v of t is equal to v1 of t plus v2 of t. So we have seen that the period of such a function could be expressed as capital T is equal to, that is capital T is equal to n1 t1 plus n, which is equal to n2 t2. Okay. So all sum of all periodic functions need not be a periodic function. So there is a mechanism with which we can check whether the sum of two or more periodic functions is going to be periodic or not. So the check is that you have to take the ratio of the periods of the individual function and see whether it could be expressed as ratios of integers. Okay. Or in other words, if you take two any one ratio, then it should be a rational number. If any of the ratio is not a rational number, then we cannot express the sum of such periodic functions as another new periodic function. So it is not possible. Okay. So then I have explained what are irrational numbers. So if you remember these irrational numbers, so you can remember whether this ratio will be a rational or not. Okay. A simple exercise is convert this to, if you are having decimal numbers, then convert this to uh, whole numbers by multiplying it. So in one of the example, I have shown you how it is done. For example, when this example is given, so here a decimal value is given instead of the angle. So this is a decimal number, so which could be expressed as uh, ratio of two integers. For example, 6.28 could be written as 628 divided by 100. So then you can cancel out some common factors and express it as the lowest integer. Okay, that is important. You should cancel out and express it as the smallest integer. You cannot retain it as such like this. If you retain like this, then it will show the harmonic frequency only. That is the multiples of these frequency only. But we need the fundamental frequency, which will be the lowest ratio of the integers. Okay. After that, we have seen what are called the average value and the effective value, or otherwise called as the RMS value. So we can express, we can find out the average value of any function by using this expression. So average value is 1 upon the total time period, integral over the time period of that function with respect to t. Okay. Similarly, we can find out what is the root mean square value, which is nothing but root of the mean of the squares of the function. So it could be evaluated using this expression. Then we have shown that it is that is the there is we can see that the square of the function and the average expression will be equal to the square of the effective value. Then we did some examples. So we started with a sinusoidal function, which is given a function that is equal to Vm cos omega t plus phi. So phi is called the phase shift. Okay. And we have proved that for a sinusoidal function, we will have the average value. Okay. So we have proved that the average value of Vt is equal to 0 because it's a sinusoidal function. So whenever you have a function like v of t is equal to Vm cos omega t plus minus phi, or Vm sin omega t plus minus phi, its average value will always be equal to 0. Because I have explained that summation integration is nothing but summation of the areas that under the function. So we have positive and negative, which will get cancelled. So we'll have average value is equal to 0. Okay. Whereas for the RMS value or the effective value will be equal to half of this value, the half of the peak of the values, right? So we have proved this. This is equal to, sorry, Vm by root 2. always remember that the RMS value of a sinusoidal function is equal to the peak value by root 2. Okay, so it is equal to Vm by root 2. Then the next example, we have seen what happens to a half rectified sinusoidal function. So the function is written like this. So for up to t by 2, we have the value. Then beyond, between t by 2 and t, we have the waveform is clipped. So this is called a half rectified sinusoidal function. In such a case, the average value will be there, because it is like we have only positive areas here. The negative areas are clipped out, so we will have some average value. It won't be equal to 0. So the average value of a half rectified sinusoidal function is hope you remember that it is equal to Vm by uh, Vm by pi, not Vm by 2 pi, it's Vm by pi. So we have derived this here. Okay. So the average value of a half rectified sinusoidal function is equal to Vm by pi. So it is sufficient that in some numericals you remember the result only. Okay. And the RMS value, VRMS, is equal to Vm by 2. Okay. So for a half rectified value, rectified function, it is equal to Vm by 2. Whereas for full, for a sinusoidal function, that is a full form, it is equal to Vm by root 2. Okay. So this we have derived. That is the RMS value of the half wave, half rectified sinusoidal function is equal to Vm by 2. And I have told you to predict what is the result of a full rectified function. If it is a full rectified or fully rectified function, then we will have the average value V of t is equal to, the average value of V of t is equal to 2 Vm by pi, and VRMS will be equal to Vm. Okay, so this will prove towards the end of this today's class. After that, we have taken one example in which a periodic function is given. So it is a square wave. As you can see, only thing you have to know how the intervals for integration are taken. So you know how the expression to take the to find the average and the RMS value. So for this particular function, we know that the pulse is having a value which is equal to s v naught up to a time period t1, and it is having a value equal to minus of v naught for the remaining period, the part of the period that is up to 3t1. So accordingly, you have to split the integral. So the total time period is equal to 3t1. So in our formula for the average value, this formula, that this t has to be replaced with 3t1. Also, the for integration part, the interval 0 to the total time period, this will be equal to 3t1. So that is split into two parts, because for one part that is up to 0 to t1, it is up to here we have the value of the function equal to v naught, and for the remaining period, that is t1 to 3t1, it is having a value equal to minus v naught. Then you can use the mathematics to integrate it and find out the value. Similarly, you can do for the in order to find out the effective value using this formula, and we have arrived at the results. Then we so the application of the average value and the RMS value. In the case of a resistor, a current is flowing through the resistor. So what is happening here? So an alternating or a time varying voltage is applied across a resistor, and some current is flowing through this, and we have found out what is the average power that is dissipated over the entire period. Okay, so So that we have found out, which is equal to, we know that the power, instantaneous power is equal to v square by r, the instantaneous power. Now if you can integrate this power over the entire cycle, then we will get the average power using this formula, the formula for the average power, average value. Okay. Then what we have done is we have replaced, instead of this time varying voltage, we have replaced it with a DC voltage, which is given by VDC, and such that the total power dissipated in the second case is equal to the power dissipated in the earlier case. And we have seen that the DC voltage that should be applied is equal to the RMS value of the uh, RMS value of the time varying voltage that we have already applied. So that thing you have to remember. So what is meant by the RMS value? We can have a definition for the RMS value of voltage as that particular voltage which, when applied across the resistor, produces the same uh, heating, or it dissipates the same power as that is dissipated by an equivalent DC voltage. Okay, so that is the definition of the, another definition of the RMS value. So we have mathematically proved that the RMS value is equal to the DC value. Okay, RMS value is defined for a time varying signal only. It is not defined for a DC value. Okay. After that, we have taken the case of a capacitor that is charging. So this is the example in which a current is flowing through a capacitor. So we have a capacitor whose value is given as equal to 1 microfarad, and the current is given as a time varying current. So it has got a pulse square wave kind of shape, which varies from +4 to -2 ampere, sorry, +4 milliampere to -2 milliampere, and the time is given in millisecond. So this current is flowing, and we have found out what is the voltage across this capacitor, which is given by V AC, small v AC, across the capacitor at t is equal to 5 millisecond. Okay, so a constant current is flowing. It is sorry, it is not a constant current. It is a pulse or a square shaped current is flowing through this capacitor, and we are asked what is the net voltage after certain time intervals, like what is the total current, sorry, what is the total voltage at t is equal to 5 millisecond, t is equal to 10 millisecond, like that. Okay, so we have seen that the expression that we have to use is the voltage across the capacitor is given by equal to Vc is equal to 1 by c integral it dt. So in order to find out what is this voltage, we need to write an expression for the current, that is it. So it is shown in as a graphical form. So if you know how to write the current, then you will be able to solve this integral and find out what is the Vc, and put certain values for the limits of the integral to find out what is the voltage at various time instances. Okay, so this current is having a particular value of 4 milliampere for time interval 0 to 3 millisecond, and it is having a value of -2 milliampere for time interval 3 millisecond to 5 millisecond. So using that, you can integrate this function with respect to t, and you can hence find out what is the voltage across the capacitor. So we have found it equal to, say we got a value as 8 volt in that example. Now the second part of the question asked us to replace this current with a constant current source. So we have replaced this, instead of a time varying current source, we have now replaced it with a constant current source. So IDC. So I represent it with the capital letter. So what is this current so what is the value of this current, so that we will have the same voltage that we have obtained in the earlier case. Okay, what should be the value of this current? So VAC is the voltage across the capacitor. Okay, so what should be the value of this current? And we were able to mathematically prove that this IDC should be equal to the average value of the average value of the time varying current that we have applied in the earlier case. So this is what we have proved. Okay, so to develop the same voltage, that is the 8 volt across the capacitor, we should uh, apply the average value of this current. So we got the current. So we have found out what is the current through the capacitor, the constant current through the capacitor IDC. It should pass through the capacitor to bring it to the same voltage, which is equal to 8 volt. And we have found that the current, this same DC current, is nothing but equal to the average value of the current function that we have already seen. So this is the average value we have calculated using this formula. Okay, so we can see that this is the uh, average value of the current, and that should is equal to the same as that of the DC value of the current. Okay, so hope you will remember this. Okay, so we can write IDC is equal to the average value of the time varying current. Hope you understand the relevance of these two examples. So one is we are equating the power, the other we are equating the voltage. Okay, so the current is equal to the average value of the current, whereas for when you are equating the power, then the DC value is equal to the RMS value of the uh, voltage or current that we are taking. Okay, so any doubt till that portion, till that section, till that example? So you have to do a lot of numerical problem related to this so that the concept will be clear. So once the concept is clear, then you can take up any different problems. So as you know, in gate variety of problems similar to this will be there. So the basic concepts are more important. So if you know the basic concepts and you know how to apply this and have the confidence to solve the numerical problem, then you will be able to score very high marks. And towards the evening class, later part of the class, we have seen we have started with non-periodic functions. So the most common function is the unit step function, which is defined for uh, t greater than which is defined like this. So it is unit step function is having a value equal to 0 for t less than 0, and is having a value equal to 1 for t greater than 0, and it is not defined for t is equal to 0. Also I had told like you can do that delay operation and advance operation. So you can delay this unit step function by uh, writing it as u of t minus tau, or you can advance this function by writing as u of t plus tau. Also you can do another operation u of minus t also, which is nothing but you're shifting this voltage towards the negative time. So this is also you can do. Lot of operations are possible, which you will do, of course, study in your signals and systems course. Also, you can shift it like towards the right also, like u of t minus, sorry, u of minus t minus 2 also you can do. In which case, this time inverted signal will shift towards the right up to the point 2. Okay, so this is nothing but u of minus of t plus tau. So it is just like we are having u of t plus tau, which is inverted. So this is your u of uh, okay. You have to check this whether it is like this or not. So I think it is like this because you are shifting, inverting this t plus tau. So it should be like this. Okay, let's verify this. Yes, similar operations are possible. You can find in your signals and systems course, but we won't be needing all these things. So in our course, we won't be using any of these functions. So that will be studied in your DSP course. So we'll be mostly using this kind of signal, that is u of t. Then we'll do u of t minus tau, and sometimes you will have to do u of t plus tau also. Okay. Another method also is available. I will explain because in one of the example. Okay. Example, we have used this function also. So when it comes, I will explain it once again. So we have already completed that problem. Now this circuit explains the relevance of studying the standard non-periodic function. So this is the typical scenario in which we have a voltage source V naught and a switch is attached, and we can throw the switch to various positions at various time instances. So initially the switch is at position 1, in which case the points A and B were shorted, and we were asked what is the voltage across the point AB, that is VAB, and what is the voltage when the switch is thrown to position 2 at time instant t is equal to 0. Such a situation in which a physical device like a switch is involved, we can model such a network uh, for our analysis purpose using this function, that is u of t. So this model could be represented by V a voltage source which is equal to V naught into U of t. So like I said, we can multiply this unit step function with a constant amplitude, so that it will go to it will have an amplitude equal to V naught. So since the switch is thrown at t is equal to 0, this is equal to this step function is drawn from equal to t equal to 0. If the switch was thrown at t is equal to 1, then we have to shift it, uh, which is called time delay. So here we have delayed the function by an amount equal to 1 second. So similar uh, circuits could be modeled in the network for network analysis. So this is similar to the earlier example, in which case the switch is thrown to position 2 at time instant t is equal to t naught. So the model equivalent circuit is represented by a constant voltage source having a value v naught into u of t minus t naught. Okay. Another example, the switch is at thrown to position 2 at t is equal to 0, and the switch is thrown back to position 1 at t is equal to 5 seconds. So how can we model? Now we can model such a circuit with again a constant voltage source. Okay, such that the voltage is v equal to v naught of v naught into u of t minus u of t minus 5. So this is represented like this. Okay, so up to 5 seconds we have the voltage um, v naught. Then after that we subtract the unit step function, so that it will be equal to, it will become equal to 0. So this is the typical voltage as seen across the terminal AB when we do this operation. That is, the switch is position is thrown to position 2 and then thrown back to 1. When it is at position 2, we will get the V naught voltage, and when it is thrown back to position 1, then no voltage is coming across the terminal AB. So this is our VAB. Okay, it's VAB. Okay, that is graphed here, and this value is equal to V naught. So that explains the relevance of step function. Another example is how to represent a function that is graphed like this. Only in which case we are considering only one cycle of the sinusoidal function. So how can we graph this? Sorry, how can we write the equation, mathematical expression? So when we write sine omega t, then it will be a function like this. It will have minus t region as well as u of t. Then you will have only the positive region. The negative regions are eliminated. But we need only one cycle, so it means that we have to eliminate this region also. So what we have to do, you have to delay the unit step function by an amount equal to 2 pi, and then you have to subtract it with from the function. So this is the function that is that is graphed here. You can represent this graph using this function. Okay, so sine t into u of t minus u of t minus 2 pi. Why 2 pi? Because you can see that when t is equal to 2 pi, uh, um, after that there is no we don't want the graph to continue. Okay, then we have defined what is an unit impulse function. So unit impulse function, we have proved that it is nothing but the derivative of the unit step function as this time period for the rise becomes as it tends to 0. So as t tends to 0 and you differentiate this unit step function, what you get is called an impulse function. So the definition of this unit impulse function is equal is delta is given is represented by delta of t. It is equal to delta of t is equal to 0 for t not equal to 0. So only at t is equal to 0 it will have a value, and the area under delta t is equal to 1. So it means that integral minus infinity to plus infinity delta t dt is equal to 1. So this is the definition for an impulse function. So delta of t is equal to 0 for t not equal to 0. So it will have value only at t is equal to 0. So it will go to as t tends capital T tends to 0. What happens to 1 by t? So we have represented this as the vertical rise as equal to 1 by t. So 1 by t will tend to infinity as t tends to 0 in the denominator. Okay, so that is the definition. Then similar to the case of unit step function, you can multiply this delta function or unit impulse function with certain constants. Magnitude like a, for example, you can write it as a into delta of t. So in such case, this magnitude with which we are multiplying is called the strength of the impulse. Okay. Then we stopped with one example in which we have found out the charge across a capacitor. So when we are applying a voltage, so a voltage of the form is as shown is given. So the voltage that is rising from 0 to 10 volt during the interval 0 to t is applied, and it is remaining at 10 volt is applied across the capacitor. So what is the charge accumulated by the capacitor? So that example we have worked out. So this example, in this example, we have we know that the charge q is equal to integral of it dt, where I is the current across current flowing through the capacitor. Okay, so we need to know what is the current IC, current through the capacitor. So IC is equal to C dV by dt, that we already know, we have studied. So in order to find the charge, we should find out what is the current. In order to find out the current, we should know what is the voltage. So the voltage waveform is given here. Okay. So one method of representing the voltage is we have written here. So how we have written this voltage? We have written this voltage. So we have a positive slope like this, right? We have a positive slope like this. So the slope of this line is equal to 10 by t into t. So that is happening only up to capital T is equal to capital T. So you have to multiply it with ut and subtract u of t minus t. So we have shifted the unit function and by an amount equal to capital T, and then we have subtracted it. So we will get only this region. Okay, and to that we have to add this horizontal region also, which is represented by 10 times. So the unit step function is multiplied with a value 10, and it is starting from capital T. So you have to time shift it with a value equal to capital T. So that is 10 into u of t minus capital T. So this is one particular method of representing this voltage. Earlier I told there is one more method I will tell you. Okay, so before telling that method, what we have done in the next step is we know that the current IC is equal to derivative of C into derivative of this voltage. So we have found out the derivative with respect to time, and then we have found out what is the current. Once we got the current, we have integrated it with respect to time during the interval 0 to t, because we are interested what is the charge at the end of this time period capital T. So the limits of the integral is from 0 to capital T. So we have integrated it and we have found out the charge is equal to 1 microcoulomb. Okay, so one method, like I said, is representing the voltage like this in terms of the unit step function. That is one particular method. Or you can also represent this in another method like VCFT, that is the voltage coming across the capacitor in a mathematical form, like it is equal to 0 for t less than 0. This type of representation also we have seen earlier, and it will take the value 10 by t into t for t lying between 0 to capital T. Hope you remember this method of notation, and that will be equal to 10 volt for t greater than capital T. So this method also you can use. So when you differentiate this, you will get what is called IC of t. So IC of t is equal to C dV by dt. So you have to differentiate. So multiply this with C, then differentiate the remaining portion. So derivative of 0 is 0, and this will be t less than 0, and it will have the value 10 by capital T for t lying between 0 to capital T, and differentiate derivative of 10 is equal to 0 for t greater than t. So this method also you can use. Okay, now you got IC of t. So once you got IC of t is equal to C into 10 by t, then you can integrate from 0 to capital T, which will return the same value. Here this is the C value, and this is the IC of t, which is equal to 10 by t, and integrate it from 0 to capital T. Then you will get the charge. Okay. So that is one method. Or since the final voltage is known, so we know what is the voltage across the capacitor at t is equal to capital T, which is equal to 10 volt. We have another expression to find the charge, which is equal to Q is equal to C into V, which we can use readily to find out what is the charge. So this step we have done is to understand how we can take the integral. Also, it is asked what is the current that is required to bring about the same amount of charge across the capacitor at as t capital T is reduced to is taking various values like 1 second, 1 millisecond, 1 microsecond, etc. So once you write the expression for IC of t, then you can readily substitute it here. Okay. So remember that these are all mm, okay. So you can substitute t capital T is equal to 1 second, 1 millisecond, and 1 microsecond, and find out what are the values of the current at various points. So we have seen that as charge is the same. So we are charging capacitor to 1 microcoulomb. So when we have smaller time, that current goes on increasing as capital T is reduced. Then we need to give more and more current to bring the capacitor to the same charge. So that is the conclusion we have arrived at. So these are the basic concepts. You have to remember. Don't forget this. If you remember this, then you can apply this to any numerical problem, because the question could be asked in any manner. So I cannot say that this question is going to be asked. So I can only tell the concepts. So this is the problem with not a problem. This is the approach you should take in competitive exams like GATE, IES, etc. You don't know. You cannot predict what is the question. Very, very, very rare cases, like less than 10% chance only some question will be repeated, or less than 5% you can guess, you can tell. But in university exam, you can say for sure that some of the question, like up to 50% probability, you can say these questions are going to be asked for the university exam. Okay. So any doubt till now, you can ask me. Okay. So moving on. Today, I want to talk to you about exponential function. So a complex okay, an exponential function is written as f of t is equal to e power st. So this s term is a complex quantity. So later towards the maybe today evening class, I will tell you what is the significance of this. This is actually a complex quantity which could be written as equal to s is equal to sigma plus j omega, which we will see in the Laplacian uh, domain, or when we see the Laplace transforms. But at present, let us say that S is having only the real part. So instead of sigma, I will be using the, as per this text, I will use the letter A. So we'll take what happens when A is, that is S is real. So we can write the exponential function f of t is equal to e power at, where A is a real quantity. Okay. Also, we have a concept called a time constant. So time constant is nothing but, if you write an exponential function as e power at, then time constant is defined as we will represent this time constant as tau. Don't get confused with the time delay that we have discussed earlier. So this is standard notation that we can see in text. So I'm using that same thing only. So tau is equal to 1 by a. So it is defined as equal to 1 by a. Okay. Because you can see when you do the dimensional analysis, you know that E is not carrying any dimension. So A is carrying the dimension of time inverse. So you can write as 1 by A as having a dimension of time. Okay. Hence the term time constant. Okay. So dimensionally, it is having the unit of time. Then another thing uh, you have to remember is, when tau is equal to 1, it is called a normalized exponential function. It's called a normalized exponential function. Okay. So it means that we will have f of t is equal to e power t only. Okay. Another situation is when a is negative. Okay. A can be positive or negative real values. So when a is negative, it is called a decaying exponential function. So it is called a decaying exponential function. See, here it is written, a decaying exponential function. Okay. So decaying. So in terms of the time constant, I can write a general decaying exponential function as equal to f of t is equal to e power minus t by tau. So this function is graphed here actually, so that will have the shape like this. So as you can see that it is having a particular value at t is equal to 0, and it is decaying to 0 as t tends to infinity. Hence the term it is called decaying function. Okay, decaying exponential function. It is exponentially decaying. It is not linearly decaying. It is exponentially decaying. Okay, so that is you have to remember here. Also, for various values, for example, what is the value of this function at t is equal to 0, which is represented by f of 0. So when you substitute t is equal to 0, it will be having a value e power 0, which is equal to 1. So as you can see in the graph, the exponential is starting at t is equal to 1, at 1 at t is equal to 0. Then another point of interest is what is happening when t is equal to tau. So what is the value of f of tau? When you substitute small t is equal to tau here in this um, function, you can see that it is equal to um, e power minus 1, which is having a value equal to 0.368. So that is a significant point of interest. So when the value of the exponential function at its first time constant is equal to 36.8 percentage of the total value. Okay, or to find out what is the value, multiply the final value with 0.368 to find out what is the value at this particular point. Okay, similarly when t is equal to twice the time constant, then it will have e power minus 2 value, which is also a constant. So that is equal to 0.135. So using this method you can plot any exponential function, or you can find the corresponding values at each of these multiples of the time constant. So that is the significance of time constant. So with this theory, you should be able to understand and define what is meant by time constant of an exponential function. Similarly, you can have an exponentially rising function also, when you which will have the shape. Okay, let me draw just below this. So it will start from particular value which is equal to 1, and it will rise and it will go to infinity as t tends to infinity. So this is the graph for v of t is equal to e power t by tau, in which we are having positive values of a. So this is vt. Similarly, the values of this function could be found out. Let me draw it in a more understandable manner. Okay, so that you can see the variation here. Okay, okay, so what happens at t is equal to tau, then this particular value will be equal to e power 1. Okay, and the value of this function at 2 tau, this particular value will be e square of the initial value, like that, assuming that it is starting from 1. Okay, so this way you can approximately plot the graph also. Okay, let's move on. Another significance of this time constant is represented by this example. So in this example, you are asked to show that the tangent to the graph of e power minus t by tau at t is equal to 0 intersects the t-axis at t is equal to tau. So what is the meaning of this question is that you draw a tangent to this exponential function e power minus t by tau at t is equal to 0, that is at this point. You can see that this tangent is going to meet this axis, that is the time axis at t is equal to tau. So can you prove this mathematically? So I will quickly tell you. to get the flavor of this thing. So our function f of t is equal to e power at. Sorry, let us write it in terms of the time constant. Okay, this is equal to e power minus t by 2. So this is the function. So this is this function. Okay. Now the tangent is a point in this function. Okay, it's touching this function. Okay, so we have to draw the tangent at point t is equal to 0. So what is the value of this function at t is equal to 0? So that will be the y-intercept of this line. So this is a straight line. This tangent is a straight line, right? So it will have some y-intercept which is given by this. Okay, so let me call this as c, the y-intercept, and it is having a slope also, right? It is having a slope. So once you know all these two values, you can write it in the form of a equation of a straight line, which is equal to y is equal to mx plus c. If you are familiar with this expression, where c is called the y-intercept and m is called the slope of this line. Okay. So in order to find what is the y-intercept, so this is the y-intercept, right? It is crossing. This line is crossing the y-axis. So it is at the point when t is equal to 0. So that will be c is equal to f of 0, which will be equal to e power minus, sorry, e power 0, which is equal to 1. Okay. So we got what is the value of c to be substituted in the equation, right? And we need to find out what is the slope of this line. So what is the slope of this line? So the slope of this line is the slope of this tangent at t is equal to 0. So this is t is equal to 0 point. So we know that the slope of a tangent could is nothing but the derivative of this function. I hope you have studied in your mathematics that the slope of the derivative of a function is equal to the slope of the tangent, right? Have you studied it or not? Are you following? How can I find the slope of a tangent? You only have to differentiate that function.
Yes,
Okay.
sir.
Yeah. So if I can differentiate quantity is t, then it will give the slope of the tangent. But we need the slope of the tangent at t is equal to 0. Then once you find the derivative, then substitute t is equal to 0, then you will get the slope of the tangent at this particular point. Okay. The tangent at various points of this graph will have various slopes. Okay, as you can see, it is having various slopes. But we are interested only in the slope at here because we are writing the equation of the tangent at t is equal to 0. So we need m corresponding to t is equal to 0. So what is df by dt? It will be d by dt of e power minus t by 2. Is nothing but e power minus t by 2. What is the derivative of e power x? It is e power x, right? And differentiate this quantity also, right? So that will be equal to minus 1 by 2. Remember, how can I differentiate e power minus t by 2? First differentiate e power minus t by 2, which is equal to e power minus t by 2. Then differentiate minus t by 2, which is equal to minus 1 by 2. Right? Because we are differentiating with respect to time. Now what is, therefore, so this is the slope of the tangent. Tangent of f of t. Okay. We are interested in the slope of the tangent of f of t at t is equal to 0. So we know what is the slope of the tangent. So substitute t is equal to 0 in this expression, so that when you substitute t is equal to 0, what will happen to e power 0? It will be equal to 1, right? So what remains is minus 1 by 2. Now I can write what is the equation of the tangent. Now, equation of the tangent, let me call it as L of t. Okay, the equation of the tangent L of t is given by this form. Okay, slope into, what is the slope? My slope is equal to minus 1 by 2. Equation of the tangent at t is equal to 0. Remember that I am drawing the tangent at t is equal to 0. So that is given by L of t is equal to minus t by 2 into the independent quantity, that is the time, plus the y-intercept. So y-intercept I have already found out at equal to is equal to 1 here. So this is equation number 1 and this is equation number 2. This is my m. Okay. So I have written m into t plus the y-intercept, which is equal to 1. So this is my equation of the tangent. So that is the equation of this line. Okay. So I have drawn the equation of this line. The tangent of this e power minus t by 2 at t is equal to 0. Now what is asked? We have to prove that this tangent, that is the tangent to the graph of e power minus t by 2 at t is equal to 0, intersects the t-axis at t is equal to 2. Now I should find what is the value of this line at the t-axis. So this is the t-axis. So what is the equation of the t-axis? If you remember in your mathematics, let me draw the axis. So if this is the y-axis and this is the x-axis, what's the equation of the x-axis? Equation of x-axis is y is equal to 0, if you remember like that. What is the equation of y-axis? Equation of y-axis is x is equal to 0, right? So these are basic mathematics. Just refresh these so that you will understand what I am trying to say here. So now I have to find out what is the equation of this tangent at t is equal to 0. Okay. So, sorry, I have to find out what is the value of this, uh, sorry, at what point of time does this line cross the t-axis? That is what I have to find. Okay. So, what is, so I have to find out at what point. So, this tangent crosses uh, at what point this line, the tangent to this graph crosses the t-axis. Okay. So, what is the equation of the t-axis? So similar, based on this analogy, I can write the equation of the t-axis as equal to L of t is equal to 0. That is the y-axis equal to 0. So if I substitute this result here in this equation, then I will know at what point does this line cross the t is equal to 0 point, right? Okay. Or another analogy I will tell you. This is the line that we are interested in, and this line is having certain L of t values, right? It is having certain L of t values. So let me call this as L of t. So this is assume that it is a function. It is having certain values L of t, which is given by this equation. This taking certain values. So when this function crosses this t-axis, what is the value of L of t? So what is the value corresponding to this? That will be equal to 0, right? So L of t is equal to 0 at this particular point. So when I substitute that L of t is equal to 0 here and find out what is the corresponding t value, that is the uh, value here. So you can prove then you can rearrange this and find out what is at what t does this line cross the time axis. So this will be equal to -1 into minus tau, which is equal to tau. So this is yet another significance of this term called the time constant. Okay, tau. So uh, so at the time constant tau, the tangent to the graph at t is equal to 0 crosses the t infinity value. Okay, uh, value of this function corresponding to t is equal to infinity. So 0 is the value of this function at t tends to infinity. Okay, as t tends to infinity, this value of the function, that is e power minus t by tau, is going to tend to 0. Okay, sorry, t tends to infinity. So as t tends to infinity, then e power minus t by tau tends to 0. So I hope that concept is clear. So that is the concept of time constant. Okay, so it was mentioned in the second year syllabus towards the end of the first module in unit 1. So when you are asked about time constant, then you have to mention all these things. Now moving on, uh, for the next level, we don't need we need to remember what is time constant. So based on this, some questions are asked, you should be able to answer with this concept that we have discussed. So once that concept is clear, you can answer any of the questions. So if we are given the initial value, final value of the of an exponential function, then how can we write the mathematical expression for that function that is given here? So we can write any exponential function as equal to f of t is equal to e power minus at plus b. Okay, where a we have already told, which is equal to the time constant, inverse of the time constant, because tau is the time constant. So a is equal to 1 by tau. Similarly, b is the final value. So final value could be represented as equal to f of infinity. So as t tends to infinity, uh, the value of this function tends to be, okay, as you can see. So this is e power minus infinity, which is 1 by infinity. So which will tend to 0 as t tends to infinity. So this term a e power minus at will vanish. So what remains is that f of infinity is equal to b. Similarly, a is given by the initial value minus the final value. So a is equal to initial value is f of 0 minus final value is f of infinity. So using this expression, you can find out what is a, b, and small a. Okay, so once you are given the time constant, you can find out, evaluate what is a. Then you can readily write the exponential function using this expression. Okay. Similarly, you can use this equation to find out what is the initial value. If you want to graph this exponential value, then you need to know from where the graph is going to start. So you need to know what is f of 0. So if you are given the function, you can find out f of 0 is equal to a plus f infinity. That is the a constant, that whatever is attached to the e power minus at, to that you have to add the final value. Okay, and you can find out what is the initial value. This will be understood if you see one example. So in this question, you are asked to find a function v of t which exponentially decays from 5 volt to at t is equal to 0 to 1 volt at t is equal to infinity. So when such a thing is given, and the time constant is also given as equal to 3 seconds. So when you observe this question, we have to find what is vt. So the initial value f of 0 is given as equal to 5 volt. So this is nothing but our b value. So you know the general expression f of t, v of t could be written as equal to a e power minus at plus b. So this is the general expression of the exponential value, where we need to find what is b, what is a, and what is small a. Okay, so we already got the value b, and the value of this function is equal to 1 volt at t is equal to infinity. So we have f infinity is equal to 1 volt. Okay. And also we should know that b is equal to f of infinity, and a is equal to initial value minus final value, that is f0 minus f infinity, right? So what is our a? So a is equal to f0 minus f infinity. So f of 0 is equal to 5 volt minus f infinity is equal to 1, that is equal to 4. And what is that time constant? Time constant is 3 seconds, right? So what is a? A is equal to 1 by the time constant. So that is equal to 1 by 3. So this is tau. Tau is given as equal to 3 seconds. So once you find what is a, what is b, and what is small a, then you can write the mathematical expression for this voltage as equal to a e power. So a is 4 e power minus, and the small a is 1 by 3. So we will have t by 3 plus b is equal to 5 volt. So this way you can write what is the voltage. So that was the significance of the previous slide. So once you know the initial value and final values, you can readily write what is the value of this function. Okay, I hope it is clear. Any doubts here?
No, sir.
Okay. If you have no doubts, then try to answer this question. Find a function Vt which decays exponentially from 5 volt at t is equal to 0 to 1 volt at t is equal to infinity. Okay, this is not a new question. This is the graph to understand, for making you understand this what here we have written in the previous slide. So I will write it here once again. The value of this function v of t is equal to 4 e power minus t by 3 plus 1. This is the function that we have. Plus 5. 4 e power minus t by 3 plus 5. Sorry, this is 5. So this should be 1, right? I made a mistake here. Nobody corrected me. Value of v is equal to I made a total mistake here, right? What is b? B is not v is equal to f infinity, right? B is f infinity. Okay. Nobody corrected me. So this is b. Okay. Remaining things remain correct. So this should be 4 e power minus t by 3 plus 1. Okay. So this is the function v of t is equal to 4 e power minus t by 3 plus 1. Okay. So what is the initial value? I told here a, this is a, and this is b. So a is equal to initial value f0 minus the final value f infinity. So we can find f0. F0 is equal to a plus f infinity, right? F infinity is b. So this is our b. So A is equal to 4 and B is equal to 1. So that is equal to 5. So the graph should start at V of t is equal to 5 at t corresponding to 0, and it will settle at 1 volt, sorry, 1 at t tends to infinity. So as t tends to infinity, it will settle at 1. And this height will be equal to 5 minus 1, which is equal to 4. So this is having a height equal to 4. Okay. Now the significance of the time constant comes here. So when you draw a tangent here, so that tangent will go like this. Okay. Only thing, you have to shift the final value. That is, this is B. So you shift it, and you can see that the tangent at t is equal to 0 crosses this shifted uh, value at this particular point, which is the time constant. So this is the time constant tau, which is equal to 3 seconds. So when you plot this towards the left, so we will get this height. This height is nothing but 4 into 0.368. So what is this? This is our e power minus 1. Okay. So this way you can find out the value of this function at a point equal to tau. Similarly, if you so this is 3 and let's say 4, 5, 6, and this will be 2 tau, and you can plot like this. So this will be equal to e power minus 2 times 4. So this height also you can find out. That will be equal to e power minus 2 times the total value, that is this 4. Okay. Now moving on to the concept of damped sinusoids. Okay. So when we multiply a sinusoidal function with e power minus t, what we get is called a damped sinusoid. So if you want to plot it, actually it is containing a cosine term also, as well as an exponential term. Since the a is negative, so we will have damped exponentially decaying function here. If a was positive, then it will be exponentially increasing function. So it will be equivalent to an undamped oscillation, in which the amplitude will go on increasing. So it will be the function will have a value inside a envelope as shown, which will be equal to e power minus 80. Actually, it is a e power minus 80. So the maximum value of this function will be at v of t is equal to a. So this will start at a, and since it is a cosine function, it will have shape like this. Okay, so it will go like this, like this. As t progresses, the amplitude goes on reducing like this. Okay, like that you can you will have. So this is called a damped sinusoidal function, and phase shift of phi. So actually, it is phase shifted with plus phi. So actually, there should be a phase shift. It will start at here. So it will have a peak value at certain that is a value at certain phase shift. So this is going to correspond to, if this is the theta axis, then this will correspond to phi. If it is t time domain axis, then phi will correspond to equal to omega times the time period. Okay, omega times tau. Let me call this as tau. If I am calling this as tau, that phi will correspond to omega tau. From where I got this? I got this from this expression, tau is equal to theta by omega. From here I obtained this. Here theta is equal to phi. Also, the omega corresponds to the angular velocity of this wave. So it is also related to the frequency, which is equal to 2 pi into f. So that is a damped sinusoid. One example related to this numerical problem you can understand here. So in this question, we are given a current. The current I is equal to I naught e power minus 80 cos omega t passes through a series RL circuit. Okay, and we have to find VRL, the voltage across this combination. So you can try out this question now. So to better understand this, I will draw the circuit diagram. So a current, we have a current source. It is passing through a series combination of R and L. Okay. So we have a resistor R and we have an inductor L. This is series combination. So it is connected in series, and a current is flowing through this. So this is I of t, which is given by the function I of t is equal to I naught e power minus 80 cos omega t. Okay. So it is varying as a cosine function. It's a damped cosine. As you can see, there is an e power minus 80 attached to the cosine function or the sinusoidal function. And we are asked what is the voltage across these combination. So let me mark the voltage across this resistor as VR, small VR, which is the instantaneous value of the voltage, and the voltage across the inductor as VL, a small VL. So what is VRL? VRL is the total voltage across the combination. So this is part A of the question. Okay. Find VRL, the voltage across the combination of this resistor. So what is VR? It's the total voltage, right? If you find what is VR and what is VL, you can add it up to find out what is VR. Sorry, VRL. So this L and this VRL, this VRL. Okay. So this is the question. Okay. So we have to find out what is the voltage across the resistor. So what is the voltage across the resistor? If current is given, it is nothing but current into the resistance value, right? So VR of t is equal to R into IT. So that will be equal to I naught R e power minus 80 cos omega t, right? So the current is not going undergoing any phase shift here. As you can see, it is simply multiplied with a constant, and there occurs no phase shift uh, in the original current. Okay, so the voltage and current are in phase in when it is passing through a resistor. Now, what about VL? What is the voltage across an inductor? If current is known, anybody? What is the voltage across an inductor? Voltage across an inductor is given by L di by dt, right? So that is equal to L into d by dt of this quantity, right? I naught r e power minus at cos omega t. Now differentiate it. Take out I naught into r outside because this is a constant. So what remains is d by dt of e power minus at cos omega t. Derivative by parts, differentiate it. So what is the derivative of e power minus at cos omega t? First part into derivative of the second part. So that will be minus omega sin omega t plus second part into derivative of the first, right? Cos omega t into derivative of e power minus at. So that will be so
minus a
derivative minus a e power minus at. Let's rearrange this and how can you write this? So minus is there in for first part as well as the second part. So I can take that minus outside. So I can write this as minus I naught into RL. Sorry, where did this R come? Sorry. Here there is no R here, right? Because we are differentiating the current here. So this is the quantity that we have to differentiate. I accidentally took the voltage. I accidentally took this thing. So don't take that. You have to differentiate the current. So this is d by dt of e power minus at cos omega t. So R won't be here, won't be here. Okay. So minus I naught L e power minus at you can pull out. There is one e power at here and e power at. And what remains is here you multiply with cos a with cos omega t. So we have a cos omega t plus omega sin omega t. Okay. Now we can write what is the total voltage VRL, which is equal to VR plus VL. So VR we have found out to be equal to this thing, right? Different color here. So VRL I can write equal to this is the equation VR plus VL. So VR I have found here and VL is this expression. So that is equal to I naught into R power minus 80 cos omega t minus I naught L e power minus 80 into a cos omega t plus omega sin omega t. If you take out certain terms, again common factor here. For similarly, here you have I naught into e power minus 80 common in the first term and the second term. So I can pull it out of a common bracket. I naught e power minus 80 what remains here is we have r cos omega t here and here we have A into L cos omega t, right? So with a negative sign. So that will be R minus A cos LA cos omega t, right? So that will be R minus LA into cos omega t, and here we have L omega sin omega t minus this L, and this L and this omega will be multiplied and sin omega t minus L omega sin omega t. Okay, so why I wrote like this is because now in order to with respect to the current that we are applying. So we are applying a current of I of t across this series combination of R and L. I need to bring it to a form like this. Okay, some cosine function or some sine function. Okay, that is in terms of a sinusoidal function. I had to bring it. So I'm going to rely on a trigonometric mm, result that may be familiar to you. So if you have an trigonometric relation like a cos theta plus b sine theta, then you can express this as equal to a cos of theta plus phi. Anybody who is interested can tell me how this result is arrived. If you remember this, where a could be written as equal to root of a square plus b square, and phi could be written as equal to tan inverse of b by a. Anybody remember how it is written? Okay, I will tell you. I will give you some clue how it is written. You can try it as an exercise. Because for gate exam, you need to study mathematics also, right? For maths, you need all this. Because some portion of the test, mathematics is carrying some marks. Without maths, you cannot get a good score. Or in short, I will tell you, mathematics is the area where in gate exam you can score maximum marks. Okay. The clue I'm going to give you is you can express this A and B in terms of if I can express this as equal to some cos of phi, let us say, and this could be written as also equal to cos of or sine of phi. Okay, this is cos of phi and this is sine of phi. Then it will be of the form cos A cos B plus sine A sine B, which could be written as cos of A plus B. So that is the clue I can give you. So once you write like this, then you can simplify and write this as a cos of theta plus phi. Once you find out what is phi, so similar treatment could be done here also. So I'll simply write out the result here. So once you do that, then I can write this as equal to I naught into e power minus at into a cos omega t plus phi. Okay, where a is equal to root of r minus la. Here the small a is replaced by r minus la, the whole square, and v is replaced by l omega. So it will be l omega the whole square. Okay, and phi is equal to tan inverse of b by a, right? So here b is equal to l omega and a is equal to r minus la. So I can write like this, or I can more simplify this by multiplying this I naught into a as having a dimension of voltage. Because if you see, if you do the dimensional analysis here, you can see that e power 80 is a dimensionless quantity and cos of some value is also a dimensionless quantity. So whatever here I have I naught is having a dimension of current, and into A should have dimension of the voltage, right? So I can write VRL is equal to, let me call it as V naught into e power minus 80 cos omega t plus phi. Also, you can see this expression that a is equal to root of r minus la the whole square plus l omega the whole square. It is having a dimension of equal to uh, ohm, okay, of resistance or reactance. So that's the dimension of this. So that current into this reactance will have a unit of volt, which is represented by V naught. So V naught is equal to I naught into A. Now, why I wrote like this is so that now we can compare this voltage across the combination of the resistor and inductor with the current that is passing through this. So when I compare this, I can see that this term you don't have to worry about this. I need to you to focus only on the phase part. That is what is happening to the phase part. Here we are having cos omega t, that is the current, and here we are having cos of omega t plus phi. So which is leading and which is lagging? So what is our conclusion we can make? So when we are having a series combination of inductor and resistor, we can see that VRL is leading. This is called a phase lead, right? When you're doing plus, it means that it is phase lead. Okay. When you're having plus values for phi, when you're having minus values of phi, it is called phase lag. So this is, we can see that VRL is leading I, IRL, we can call, because it's the same current that is passing through the inductor and the resistor by an angle phi. So that is the conclusion that we can make. Also remember that these are exponentially decaying values, okay, because we are having an e power minus 80 attached to the sinusoidal function cos omega t. So this is a damped oscillation that is happening. Now why that damping is coming is because we are having a resistor attached to this. So as a result of this resistor, so the power is getting dissipated here, okay. So when you are applying a damped oscillating current to this combination, we will get the voltage also as damped oscillation. The second part of this question tells compute VRL for I naught is equal to 3 ampere, A is equal to 2 ampere, sorry, A is equal to 2 and omega is equal to 40 radians per second, and R values are also given, and sketch I as a function of time. So once you have this expression, let's substitute all these values here in this expression for R, L, A, etc. Then you can find out the corresponding numerical value also if required. Okay. And for the sketching part, you can sketch it for simplicity. So they are asking to sketch this function. Okay, I naught t power minus 80 into cos omega t, right? So this is sketch for I of t is equal to 3 e power minus 2t. So once you substitute these values, okay, so the value of I of t is equal to I naught e power minus 80 cos omega t, right? So that is given here. I is equal to I naught e power minus 80 cos omega t. Then you substitute the value for I naught a as well as omega. Then you will get this is equal to 3 e power minus 2t cos omega is 40 t. Okay. So this function is sketched here. So why I am showing you is for so that you can understand what is happening to this function. So there is no plus or minus 5 here. So the cosine function is starting from t is equal to 0, is having a peak at here. If there was one plus or minus 5, then it would have shifted. There would have been a lead or lag correspondingly. Plus means a lead and minus means a lag. Okay, so if it was a voltage function, in which case we had a plus 5 in the this case. So this means a leading function. If you were to sketch that, then it would have started from somewhere here corresponding to the plus 5 here. Okay. Okay, since we are plotting the current, there we are looking at this function. So that is cos of 40t. So it will have the shape of a cosine function, as you can readily see. Uh, so we have a period here, complete cycle. Also, it is wrapped between this envelope, which is equal to 3 e power minus 2t. So this is the uh, peak value at which it is starting. So this is equal to 3. So this value is equal to 3, corresponding to t is equal to 0. Okay. Then it will oscillate at a frequency of omega is equal to 40 radians per second. So we have omega is equal to 40 radians per second. So what is the time period for completing one cycle? So time for one cycle. So one cycle corresponds to a total angle of 2 pi, right? Divided by the angular velocity. So that is equal to 40. So at 2 pi by 40, it will complete one complete period, right? One full cycle, right? So that is equal to pi by 20. It will complete one full cycle. As you can see, at this pi by 20 value, it has completed one full cycle. So starting from here and then ending here. So that is the relevance of pi by 20. This is given from the angular frequency or angular velocity. Also, one more thing, the time constant t is equal to 1 by a. So a is given as equal to 2 here. So that will be equal to 1 by 2, which is equal to 0.5. So what is the significance of this? I have already explained. So when we have an exponential function 3 e power minus 2t, which is having the shape like this, and I draw a tangent at t is equal to 0, then this tangent is now going to meet the time axis at tau here. So this is tau, which is equal to zero point 0.5, right? So that is the significance of the time constant 0.5. And what will be the value of this function? What will be the value? So if I draw a vertical like this, what will be the value of this envelope here? What is this height? Can anybody say what is this height?
1.5 around something.
How can it be 1.5? How did you get that value 1.5? Maybe your answer is correct, but I want you to tell me how you arrived at that result. Because I did not calculate the value. Maybe it is 1.5. So that could be arrived at the concept of tau, right? Because I said at t is equal to 1 time tau, then the value of this exponential would have dropped to equal to e power minus 1 times the initial value. Okay, so this value will be equal to 3 into e power minus 1. So that should be equal to 30 percentage of this. Okay, so that will be 3 into 0.368. So you are telling, if you are telling that this is equal to 1.5 around, then it is correct. Okay. So this will be equal to I of tau. So that is equal to uh, 0.368 times I naught. Okay. So in our example, I naught is equal to 3 ampere. So that will be equal to 0.368 into 3. Okay. So all these are the things I wanted to explain here. I hope the concept of damped oscillation is clear to you by now.
Yes, sir.
Consider this question. Find the maximum and minimum values of V is equal to 1 plus 2 sine omega t plus theta. So we are adding a constant value 1 to a sinusoidal function. So what is the maximum value it can achieve? So it can achieve a maximum value V max, which is equal to 1 plus the peak value of this. Okay, so we are adding uh, these two functions. So this is V is equal to 1 is this function, and so this is V, then this is V is equal to 1, and to this function I am adding 2 sine omega t. Okay, so this is 2, this is 2, and this is the function V is equal to 2 sine omega t plus theta. Actually I should draw this function like this because it's showing a phase. It's showing phase lead, right? Okay, so this is theta. Anyway, the peak value is, this is going to correspond to theta. So this is going to correspond to theta. So that should be equal to t is equal to theta by omega. Okay. So when I add this, so what happens to this voltage is this will get shifted by a magnitude equal to 1 here. So it will have a magnitude peak value of V max is equal to 1 plus the peak value of this function, which is 2. So it will be equal to 1 plus 2, which is equal to 3. And the minimum value is, since it is shifted by 1, then I will have a minimum value of 1 minus 2, which is equal to minus 1. So as you can see, when this voltage, this is corresponding to minus 2. So if it is shifted by 1 unit here, then this point will be clipped here. So I will draw the final graph. I can draw the final graph here. So when you add both these two functions, the entire thing would have shifted to like this. There won't be any change in the shape or in the frequency. So all these points remain the same. Okay. Since I am drawing, so shape may appear somewhat distorted, but there should not be any change in shape. Okay. And now this point has shifted to 1, and this peak is going to correspond to 2, and this negative peak is going to correspond to minus 1. Sorry for the note to scale drawing, because you should understand what is the shape and the values from the marking. So this is corresponding to 2. The peak will be at 2. So that is V max, the new V max. Okay. And I am adding, and this is the new V min. And this is V min. Okay. What about the second portion? Determine if the function V is periodic and find its frequency and period t. So will it be periodic? Yeah, it will be periodic. Okay. because this is a constant value, and as you can readily see, this is also a periodic function where the period is not going to change because this is a DC or constant value that you are adding. So it is also periodic, and the frequency is not going to change. So it is so this is periodic. V is periodic, and the period is not going to change with frequency equal to omega itself, which is equal to 1000 radians per second. Okay, this theta is also given as equal to 3 radians, and t could be found by t is equal to that omega is equal to 2 pi by t. So you can find out what is t, the time period corresponding to this. It's equal to 2 pi by omega. From this, you can find out what is the period for this. Okay. And in order to specify this phase in degrees, what is the multiplication factor? Can you convert this radians to degree? The factor is 180 divided by pi to convert radians to degrees. Okay. I hope you have studied this in your mathematics. Okay. So multiply the radian value into 180 by pi to convert to degree. To convert it back to a degree value back to radians, multiply the degree value with pi by 180. Okay, so that is the answer for this question. This is a question similar to that I have given you in an earlier exercise. So find the average and effective value of V2 for this value. That is V1 is equal to 2 and V2 is equal to 1. So this is equal to minus 1. So this is minus 1. What is the average value? So quickly recalling the average value formula, that is equal to 1 by the time period. Remember that this is the time period integral over the time period of this function v2 of t dt. Okay, v2 of t dt. So this is the formula for average. Quickly tell me what is the average time period? T is given here as 4 times t1,
4
right?
T1. Yes, sir.
It is 4 t1. And tell me the limits of the integral. How can I split it? 0 to t1.
T1.
Value of the function is 2, right? Up to t1, the value of this function is 2.
2
So it is 2 dt plus integral t1 to
T
uh, t1 to here
T
it is t is equal to 4 t1. Okay.
4 T1
Okay. So this should be integral of t1 to 4 t1, and the value of this function is minus
minus
1.
1
Okay.
Minus 1.
Yes. Minus 1 dt.
T.
So we can integrate this. Straightforward integral. So it will be 2 into t1, right? Because here the upper limit is t1 and lower limit is 0, and plus minus 1 into
4 T1 minus
4t1 minus t1. Yeah, you straight away do this. So t1 will get cancelled, and finally
minus T1
you will
upon
get
4 T1.
yeah. So that will be minus 1 by 4, right?
Yes, sir.
Similarly, you can use the formula for the effective or the RMS value.
Yes, sir.
So yeah, first you square it. Effective value is otherwise called as the RMS value. Just square it. So 1 by t integral 0 to t
V square
v2 square t dt. So limits and those things are not going to change. It is going to remain the same. So it will be 3t1, 0 to t1. Instead of 2, it will be 4 dt. And instead of -1, it will be +1. That's all. t1 to 4t1 1 into, because it is -1 square. Okay. For understanding purpose, I will write this as 2 square. Okay. dt. So you should be getting it as equal to 7 by 4. See if you are getting 7 by 4. Therefore, you can write V effective or V RMS is equal to square root of 7 by 4, which is equal to root 7 by 2. That will be equal to 1.32. Okay, just verify you are getting the answer. Okay, quickly moving on to the next question. Just note down this value. If you are having any trouble, you ask me in the evening
Sir,
class
it's,
if you are not
sir,
getting
it's
this.
4T1. You have written 3T1 in the second step.
Yeah. Sorry. Here. Okay. Thank you for correction. It's 40. Okay. Okay, because time period is 41 is given here. Now moving on. This is an example of a half wave rectified sinusoidal function. By sinusoid, it means cosine or sine. It doesn't matter. Both are called as sinusoidal function. So we have already derived the expression for the average value. So we should get the value as V1, average value of V1. What is the average value of cosine wave? Half rectified cosine wave? Average value of a sinusoidal wave is equal to 0, right? Full wave. So half rectified is, I told you it is equal to Vm by pi, and the effective value is equal to Vm by 2 for half rectification. So this is for half rectified. And for sinusoidal function, that is sine omega t or cos omega t, the average value will be equal to 0, and the effective value will be equal to the peak value by root 2, Vm by root 2. And for full rectified, the average value will be equal to 2 Vm by pi, and the effective value will be equal to Vm. Okay, so this we can understand here. So tell me how you can take this function. So how can you represent this V1 of t? I had told you two methods of representing this function. First, you can use the unit step function and then multiply it and represent like that. Or another easier method also I have told you. You can represent it for intervals. Because this is a periodic wave, so I can represent uh, 2t by 4. It is like a shape of a cosine function, right? So I can write this is equal to cos omega t for t lying between 0 to t by 4, and it is carrying a value 0 from t is equal to t ranging from t by
3
4
by
to
4 to 3T by 4.
yeah 3t by
3T
4.
by 4.
Yeah, and it is having the shape of a sine omega t, right? Now this is like a sine function. for the remaining. So that will take the value of sine omega t from 3t by 4 to t. So once you can write this function like this, then you can find out what is the average value using that formula. Average value is equal to 1 by time period integral over the time period v1 of t into dt. So here the time period is capital T itself, and this integral we have to split because it is carrying various functions, various values at certain intervals. For example, from 0 to t by 4, it is having a value of cos omega t, and for this interval, it is carrying a value 0. So let us skip it because integral will also yield 0. And for the remaining portion, that is 3t by 4 to t, it is carrying a value sine omega t. So I want you to understand how these intervals are taken. In a real question, only thing this here instead of t by 4, it will be given by 3t by 3 or 4 like that. That's the only thing. So we cannot do all the possible combinations of a certain question. So once you know how a question is approached, then you should be able to deduce how to approach a different question. So see how I have taken this. A similar question we have done in an earlier case in which we represented it as a cosine function. Do you remember that question? Where I shared the result of this when I was discussing on the average and RMS value. I have discussed this. For your refreshing your memory, I will show you that slide. Quickly, I will show you that slide. This is the question I am mentioning. So this is the same question only, but only thing instead of the wave from 0 to t by 2, it is shown as it is oscillating from minus t by 2 to minus t by 4 to t by 4. Okay, that's the only thing. But the result will be the same. Okay, so I will show you that if you take the intervals correctly, it will give the same result. So that result I have written on the top of this current slide. Okay, since you should understand it's a half rectified sinusoidal function, so you should get the same result here. If you are not getting the result, then somewhere you have taken the wrong intervals or functions. Okay, you are not able to deduce the function correctly. So quickly tell me what is the integral. So it will be cos will be integral cosine will be okay. So here let me check this. Cos so sine omega t by omega. The limit is from 0 to t by 4 plus, and this sine will be equal to minus cos omega t by omega, and interval is from 3t by 4 to t. Okay, so it will be 1 by t, and omega I can pull out of this. So what is remaining is sine omega capital T by 4 plus here I have this minus, so I can do the lower limit minus upper limit. So what I am going to do is cos omega into 3t by 4, that is the lower limit, minus the upper limit, it is cos omega t. Okay, once I write this, I should know what is the time period t for a sinusoidal function. So that is equal to 2 pi, right? Or I can write omega is equal to 2 pi by t. So t is equal to 2 pi by omega. Substitute this here. So this will be omega into 2 pi by omega. And here it will be sine of omega into 2 pi by omega by 4 plus cos omega 3 into 2 pi by omega cos of 3 omega by 4 into 2 pi by omega minus cos of omega into 2 pi by omega. So it is 1 by 2 pi, and here we have sine of pi by 2 plus cos of 3 pi by 2 minus cos of 2 pi. So that will be equal to, somewhere I dropped something, right? I dropped the Vm value here. So there is one Vm here because the peak value is Vm, right? So this is Vm cos omega t, Vm sin omega t. Don't drop the amplitude, don't forget. So you have to write the function correctly, okay? So V1 is equal to Vm sin omega t or Vm cos omega t. Throughout we are having Vm, the amplitude, okay. So here we have Vm by 2 pi into, what is sin pi by 2 is equal to 1, right? Sin 90, sin pi by 2 is sin 90, which is equal to 1, right? That is cos 3 pi by 2, which is cos 90, which is equal to 0. What is cos 2 pi? Cos 2 pi is cos 0, which is equal to
1, sir. 1.
it is equal to 1.
1.
So you are getting 1 minus 1, which is equal to 0. Somewhere we have made some mistake. Where did we make mistake? Okay, I will find out and discuss in the second class. Meanwhile, you also think about this. Okay. So otherwise, we will be wasting some time. So think about where we have gone wrong. In my rush, I think I have made some mistake somewhere. Okay.
Sir, sine
Applying
omega
the,
t, the limit which is 0, I think we didn't took it.
okay.
The second
So
step.
sine 0 is 0, right? Sine 0 is 0, right? So I didn't take it. Okay, I will figure out by today 6 o'clock class. We will do solution. Okay. Meanwhile, if you want, you can. Okay. After that, we will do this portion also. The remaining questions. Then I am planning to do this more question. Okay, so I think evening also it will take the remaining time. In the remaining time, we'll do the remaining numerical problems. Then, if time permits, then we will start with the Laplace. Okay, Laplace analysis. So it's already 10 past 10. So we'll meet evening 6 o'clock. Okay. Meanwhile, if you are having facing any doubts while you do any numerical problem, just note it down. We'll have a discussion on that also. If you have any doubts, you can ask me. And if it is exceeding our time limits, then we'll conduct some extra classes to rectify your doubts as well. Like if you are solving some gate previous question paper or some numerical problem, you are not getting the answer that is given in the textbook, we can have a discussion on that. Okay, so bye for now. See you in the evening.